perhaps there's an indication, maybe the only kind of extreme event that will happen a little less intensely are cold spells in the winter. But that said, what we are seeing instead, because of the large waves happening more often in the jet stream, that cold air is penetrating into regions where they just aren't used to seeing it. So even though overall it's not as cold as it used to be, it's going places where they just can't handle it.
Hello, everyone, and welcome to the Climate Emergency Forum. My name is Regina Valdez, and I'm your host. We have a special guest with us today, Dr. Jennifer A. Francis. Our topic is weather whiplashing and Jetstream waviness. We have Dr. Francis here to discuss her paper, Measuring Weather Whiplash Events in North America, a new large-scale regime approach, on which she was lead author. She is also a senior scientist from Woodwell Climate Research Center. We're very, very lucky to have her today. Maybe a lot of you have heard rumblings of weather whiplash. It sounds rather colloquial, and one might be surprised that this is actually a sciencey term, if you will. So it's really exciting to hear what it actually means. And I'm going to leave it there so that we can hear more about this phenomenon. So, Dr. Francis, I'm really looking forward to hearing what you have to share with us today.
Well, thank you for that nice introduction, and thank you for inviting me to be here today. I'm going to jump right into my slides here. Yes, today we're talking about weather whiplash and some new work that I've been doing with a group of colleagues, both at Woodwell and elsewhere. And we'll first talk about what is it, what kinds of weather it causes or can cause, and also has it been changing and will it change in the future? So first of all, what is it? Well, there is no real definition out there that has been agreed upon by everyone, but our definition is an abrupt shift from one persistent set of weather conditions to another very different set, which often is one extreme event to another type of extreme event. So you might think about, for example, a drought that's been going on for a long time that all of a sudden is broken and there's a lot of heavy rain, for example. Or it could be a heat wave that is suddenly changed over to a cold spell in the wintertime. Or it could be as simple as just sort of dreary conditions all of a sudden being replaced by clear blue skies with breezy blue skies. So these are the kinds of weather shifts that could make up a weather whiplash. And here are some specific examples that have occurred over the last few years. Back in 2020, the Rocky Mountain states were experiencing a record summer heat wave during September, and over a period of only 18 hours, they had snow on the ground, and the temperature dropped about 60 degrees Fahrenheit. Another example, we can always look out to the West Coast for examples of weather whiplash. California had been experiencing a very long, hot, dry spell, and they even had wildfires occurring in January, which is almost unheard of. Several years of these very dry winters, it shifted in late 2020, early 2021, late January, and all of a sudden they were experiencing what you might call atmospheric rivers, very heavy precipitation events with lots of snow in the mountains. So these are the kinds of things that we describe as weather whiplash, and we've written two recent papers on this, one focused on North America and the Northeast Pacific, and the other one that just came out recently is focused on the region that includes Europe and the North Atlantic. And they both basically take the same approach, but they're focused on different parts of the globe. And here's what we are thinking about when we talk about weather whiplash. We can look at the atmosphere like you would look at a topographic map of, say, a mountainous region. And here we're looking down over the North Pole. So we can look at the atmosphere like you would look at a topographic map of land. And in this case, we're looking down on the North Pole. The continent of North America is down at the bottom there. And we know that the high elevation areas, which are colored red here, mean that the air is warm under that layer of atmosphere. So these red colors mean high elevation, just like you were looking at mountains on a topographic map of land. And where it's blue, it means that the air is cold, because air contracts when it's cold and it expands when it's warm. So this gives us a picture of what the atmosphere looks like. And in addition, we know that on a topographic map, when these lines of equal elevation are very close together, we know that it means the slope is very steep, just like the side of a very steep mountain. And this helps us because where those lines are very steep is showing where the jet stream is. The jet stream occurs where this very strong change in hot to cold in the atmosphere occurs. And you can see that those lines outline waves in the atmosphere. So we can actually look at these waves in the jet stream using this type of topographic map of the atmosphere. And this is what we're using to diagnose weather whiplash. And we really care about these waves in the jet stream because they are really what make our weather. So here's a schematic of a typical wave in the jet stream over North America. We know that the jet stream separates the cold air to the north from the warmer air to the south. So immediately you can see that if you're in Ottawa, for example, you would be on the cold side of the jet stream in this particular example. But the waves in the jet stream also create weather patterns. So where the wind in the jet stream is coming from the northwest, we tend to find high pressure, clear blue skies, no precipitation, and the atmosphere is very dry and settled. And on the other hand, this part of the wave, where the winds are coming from the southwest, is where the storminess occurs. So it's bringing a lot of tropical moisture northward, and we find a lot of storms in this part of the jet stream wave. So knowing where these waves are located and how they're going to shift is totally controlling the weather that we experience in any given location. So let's look at another example and see what the jet stream looked like during this particular weather whiplash situation. So this happened to be a freeze event that occurred in the southeastern part of the United States, in particular Florida. They saw iguanas being stunned by that cold and falling out of the trees onto the sidewalk. They had falling iguana warnings posted over highways. And here's what the jet stream looked like during that case. So you can see that it was swooping northward over the western states, bringing a lot of settled, dry, warm conditions to that part of the country. And then it took a big dip southward over the east. And that's why all this cold air plunged southward down into Florida. But only a few days later, we saw almost the exact pattern emerge. And this map here is showing you temperature differences from normal. You can now see that most of the East Coast is now breaking records in terms of warmth. All those white circles around different stations indicate broken high temperature records, while out west, just the opposite, it was cold out there. And we can see that the jet stream also has shifted dramatically, causing that change in the anomalies in the temperatures. So the jet stream is absolutely key. And so we are using these patterns in the jet stream to diagnose where weather whiplash events and when weather whiplash events have been occurring. So here's another example of that topographic map of the atmosphere. And we can see these features where there are ridges where the jet stream bulges northward and troughs where it dips southward. And you can see that the abnormal warmth and abnormal cold temperatures coincide directly with where these troughs and ridges or wave peaks and wave troughs occur around the northern hemisphere. So our approach was to look at these patterns that occur in the atmosphere. We used an AI tool called self-organizing maps to go through 72 years of daily maps of these anomalies in the topography of the upper level atmosphere and to find the characteristic patterns that naturally occur in the atmosphere. So this is based on like 25,000 days of these patterns. And so we end up with this matrix of these patterns in the atmosphere that occur naturally. And we can look at how often they occur, and we can look at also how they shift from one pattern to another, which is the whole idea behind our approach. And in this particular AI tool, as I mentioned, self-organizing maps, you see that the most similar maps are located near each other, and the most different ones are located farthest apart. So if you look at the upper left, you see the Arctic area is very warm, while the bottom right corner is just the opposite. The Arctic is very cold. So look for cases when we see more than 4 days, sequential days being in one pattern. So let's say the upper left pattern. We look for times when the atmosphere 4 days in a row looks like that pattern, belongs in that cluster of days. And then we look to see what happens to it when it leaves that pattern. So we look for cases when it jumps to a different pattern 2 days later after being stuck in one pattern. And we try to find examples where it doesn't just go to the more similar pattern, which is indicated here. This would not be considered a weather whiplash event because the pattern is too similar. But if it went from, say, the bottom left corner to that upper pattern there, that is completely opposite, and that would indicate a weather whiplash event. So the atmosphere is completely shifting from one jet stream pattern to a different jet stream pattern. And so what we found is that these weather whiplash events, where it jumps from one pattern to a very different one, occur most often when the Arctic is very warm. So when we get a stuck pattern in one of those cases where the Arctic has those red colors associated with it, and then it jumps to a very different pattern from there. And we know that the Arctic is warming very fast. So this implies that we're going to see an increase in the frequency of these weather whiplash events as the Arctic continues to warm, because that's where we find the most weather whiplash events occurring. So this is the basic idea behind what we did. We applied this not only to past atmospheric patterns using these 72 years of actual data, but we also looked at model simulations of the future, because this AI tool doesn't care. We can look at whatever patterns we want. And what we find is the trends in the frequency of these weather whiplash events increases much more rapidly in the future. And again, especially for these patterns where the Arctic is very warm. So that's what I have, and I'm happy to move into question mode here.
Thank you so much, Dr. Francis. That was really fascinating. I really liked your overlay and how you showed the jet stream and its movements and how it really does affect and essentially determine the temperature and the weather that we experience. And it seems like, as you said, that it all really, the locus of this is in the Arctic. And then what happens in the Arctic determines what happens with the jet stream. Did I get that right?
What happens in the Arctic is one factor that affects the jet stream. There are many factors, actually. Things like El Nino, which we're experiencing right now, has a huge impact on the jet stream. And there are other factors too. So it's always difficult to untangle what is causing a big shift in the jet stream, or what's causing a particular pattern in the jet stream. Oceanic heat waves is another example of factors that affect where these troughs and ridges in the jet stream set up. So it's a very complicated system, as we all know, but certainly the Arctic is playing a role. And the fact that it's warming so much faster than the rest of the globe, approximately 4 times faster than the globe as a whole these days, which is rather amazing, it's becoming more of a factor. It's competing with these other things that have existed in the past, like ENSO we know is a naturally fluctuating factor. But, you know, I have to say ocean heat waves, which are also increasing and are raging around the oceans right now also have a very important role in determining where these waves in the jet stream occur.
It's really interesting. As in nature, nothing happens in isolation. Everything affects everything else. I know that, Paul, I've spent many COPs with you in the Arctic Pavilion, so this is of great interest to you. I'd like to hear what you have to say about what Dr. Francis just shared with us.
Yes, thank you. I guess my first question is on the self-organizing maps. I think you've taken an average of the Jetstream configuration over 4 days from what it looks like to define a state. I'm wondering if I go on Earth Null School or any of the weather apps and I look at the jet streams around the planet, they often don't look anything like the idealized maps that you show. But that's we're looking at them sort of on a daily basis. So have you tried your self-organizing maps, not for 4-day average, but for like a daily average or even morning versus evening sort of variation of the jet streams to see, if some of the details in there might give you more information?
So self-organizing maps, the way it works is that it's a neural network basically, and it identifies these very characteristic patterns that occur in the jet stream or whatever your parameter is that you decide to use to, quote, train your self-organized maps. And you need to have many, many days or examples to put into the tool to get it to produce these characteristic patterns. So what you end up with is like those 12 patterns that I showed. We know exactly which day, which pattern each day in that 72-year period belongs in each of those patterns. So if you looked at any one day, it tries to find the pattern of those 12 that's most similar to the pattern on that day. So naturally, on any one day, it's not going to be exactly like that pattern, but it'll be most like that pattern. So those patterns are the average of all the days that are most similar to it. And so by looking for these persistent, what we call long duration events, which are these examples where for 4 days in a row at least is in that one single pattern, then we can start to think about, okay, what happens when it jumps to a different one and causes, it represents a weather whiplash event. So looking at an individual day, yes, it's not going to look exactly like that pattern that it belongs in, but it'll be quite similar to it.
Jennifer, I understand that about 2/3 of the heat transfer from the equator to the poles is in the atmosphere, mostly in wind patterns, and about 1/3 is in the ocean currents. Have you tried to look at changes in the ocean currents and how that correlates to changes in the jet stream patterns?
Nope, that hasn't really been something that I've looked at too much. I was part of a group that wrote a paper that came out in Science magazine recently that mostly just looked at changes of heat transport by the ocean into the Arctic and how that was affecting sea ice changes. So I'm not an oceanographer. There's enough to do in the atmosphere without looking at what's going on in the ocean. And I would say that we have less good data about the heat transport in the ocean, and we have much better idea of what's going on in the atmosphere. So
I have to ask you, in the news recently, there's been reports of airplanes flying from North America to Europe and setting record low transit times, flying at speeds, ground speeds of 820, 830 kilometers an hour, because they're riding this very, very fast part of the jet stream. So I'm trying to understand, because of the Arctic warming and other factors, we know the jet streams are slowing down and getting wavier and getting stuck in place. So how does that jive with record high jet streams for this airplane travel?
Yeah, that's a great question. So the first thing we have to understand is that there are two jet streams in the Northern Hemisphere and the Southern Hemisphere. They're not always two, but in the winter, there are often two. There's the polar jet stream and there's the subtropical jet stream. The polar jet stream is mainly driven by the difference in temperature between the Arctic and the mid-latitude, so say the middle of the United States. Whereas the subtropical jet stream is mainly driven by temperature differences between the mid-latitudes and the tropics. So those are two very separate things that are driving these jet streams. The polar jet stream is the one that is weakening. We've measured that, and it's because the Arctic is warming so much faster than mid-latitudes are. Whereas the subtropical jet stream, especially in an El Nino year, has a stronger poleward temperature difference between the mid-latitudes and the tropics. And so that's why we generally see a very strong subtropical jet stream during El Nino years. And in fact, that's exactly what's happening. And that's the main reason behind this very strong subtropical jet that is enabling airplanes to take these very fast tracks across the oceans, especially.
Great. And I have one final question before I'll pass you over back to Regina. Your papers, are you planning on repeating this work in the Southern Hemisphere? Like, there's some strange things happening in Antarctica, specifically the lack of Antarctica sea ice. And, if you look in the paleo records, often when the Arctic would cool very, very quickly, the Antarctica would warm and vice versa. It's like a seesaw effect between the two poles. But I mean, we're seeing huge warming in the Arctic, but also huge warming now in Antarctica. So, I mean, what are the jet streams doing in the Southern Hemisphere, or is that something that still needs to be studied, I guess?
Yeah, so there's a lot of change now happening in the Southern Oceans. That is very recent. It's only in the last couple of years that we've seen the Antarctic sea ice show some sign of really decreasing. Up until now, that has not been the case. It's just been very variable from one year to the next. And generally, we don't see an Antarctic amplification of temperature like we see in the Arctic. Maybe that's going to start now that the sea ice has diminished so much, but it's a very different set of circumstances down there. We don't have the same kinds of waves in the jet stream. I mean, they are not amplifying because we don't have this reduction in the polar temperature gradient. So, right now I don't have plans to look at weather whiplash type features down there, but we do know that in general, the jet streams in the Southern Hemisphere are shifting southward. And this means that places like Australia and Southern South America are seeing more frequent heat waves in the summer, more frequent droughts, because the jet stream waves are just not bringing as much cool air and precipitation to those continents. So it's a very different set of circumstances that are driving that. However, it's not that the Antarctic is warming much faster than elsewhere, although the peninsula is definitely warming quite fast, but it's not big enough to have a big impact on jet stream waves.
Thank you so much. I really appreciate those questions, Paul. And it's so interesting and so fascinating. And what I love about this program and the guests that we have on, it enables me to learn so much about a subject that I'm very interested in, which is the climate, our world, our environment. And I'm wondering how many out there knew that there were two jet streams. So if you weren't aware of that, I'm very glad that you are now, and we helped make you aware of that. And please, if you are learning something, be sure to share this video with your friends. Give it a thumbs up. And if you haven't done so, we'd like to have you join our subscribers. So please do so. And now I'm going to turn it over to Peter. Peter, what questions do you have for Dr. Francis?
Jennifer, thanks for that excellent presentation. Your images are really, really good. You're a great climate change communicator as well as a scientist, so thank you for that. I also want to thank you for the work that you've done and stuck to doing between the link of the loss of Arctic summer sea ice and disturbance of the weather and climate in the Northern Hemisphere. And that is so important because it relates, of course, to relying on predictable and sustainable food production in the Northern Hemisphere which of course have the best regions of food production. And we're already getting into trouble on that. This is a thing that has concerned me for years. For example, Europe had a major drop in crop productivity last year. So I want to thank you very much for doing that. And I guess you've noticed that we're supposed to be having or waiting for an imminent weather whiplash in the United States, and it's all over the media. The issue of whiplashes. So, of course, the difficult question is if our economy and politicians continue as they've been doing, which of course is to do nothing but keep subsidizing fossil fuels, what happens to the Northern Hemisphere with these increasing extreme weather events of all kinds and whiplashing and jet streaming? Um, uh, it's looking like a rough future. What do you think?
I would agree with you 100%. As long as we keep dumping additional heat trapping greenhouse gases into the atmosphere, we're going to see all kinds of extreme events happen more often. Perhaps there's an indication, maybe the only kind of extreme event that will happen a little less intensely are cold spells in the winter. But that said, what we are seeing instead, because of the large waves happening more often in the jet stream, that cold air is penetrating into regions where they just aren't used to seeing it. So even though overall it's not as cold as it used to be, it's going places where they just can't handle it. So places like Texas in February 2021, when they had that extreme cold spell and the frigid air went all the way down to the border with Mexico, and it completely obliterated their infrastructure. They had no heat, no electricity. So even though we see these cold spells becoming less intense overall, they're affecting places that just aren't used to dealing with it. So, but overall, yes, we're seeing all kinds of extreme events happening more often, and that's only going to get worse unless we can turn around our behavior and stop producing so many greenhouse gases and stop cutting down forests.
So yeah, and my impression is that the North American continent is particularly vulnerable to these huge continental weather disturbances. Once again, and I've noticed this several times when I look at particularly the anomaly maps of North America, how they've changed. It's almost split down the middle, and a couple of years ago it really was totally just split down the middle. Cold anomaly on one side, hot anomaly the other side. So we're looking at this again. Eastern United States is getting record temperatures, and northwest of is in the cold again. But have you noticed, because when we get this strange and dramatic change in anomalies in the North American continent, the Arctic seems to do a similar thing. It seems that on one side of the Arctic, there's a cold anomaly, and on the other side of the Arctic, there's a hot anomaly. So maybe the Arctic overall is getting the weather and climate is getting severely disrupted.
It is. I agree with you 100%. We're seeing these very strong anomalies happening in many locations. North America often tends to be split down the middle just because of the size of the continent and how it relates to the size of the jet stream waves. But it's happening in Europe and Eurasia as well. It just happens to be a much bigger continent. And so it's bigger than any one jet stream wave from one end to the other. So it is happening everywhere though. So, and it's all connected. I think, as Regina might have said in the very beginning, everything's connected, and that's absolutely true. So, and we know that what's happening in the Arctic, which is an overall general warming with hotspots in certain places that are generally co-located with where the sea ice has been disappearing the fastest. But even there, things have been unusual. So we've seen some big transports of heat northward, causing heat waves over the North Pole, they've been called, where we've had near freezing temperatures even in the middle of winter. And of course, the result of the sea ice is just not freezing as it used to in the wintertime. And we're going into this season now, we're going to be seeing the maximum extent of Arctic sea ice in the next few weeks. And it is already much thinner than it should be this time of year. So we're concerned that this coming summer could be a tough year for that sea ice. And, we're going to break a new record at some point. It hasn't been broken since 2012, but, we're running at very low amounts of sea ice, and it really just depends on the fluctuations of weather, whether we'll see something like that. But yes, it's all connected. These anomalies are getting more extreme, and it's all connected to the jet stream.
One of the things that I'm kind of interested in, and I don't know if it's related, but does the jet stream have an impact on air pollution, or does air pollution affect the jet stream in any way?
The jet stream definitely affects air pollution. So if we just look back to this past May, when you all were experiencing those terrible wildfires in just north of you in Canada, and all that smoke got transported down along the eastern seaboard of the United States and causing some of the worst toxic air conditions that we've ever seen, that was the jet stream's doing. And in fact, the jet stream also was responsible for creating the conditions that led to those terrible fires. So there was a big ridge in the jet stream all spring, and that kept the rain away from sort of north central Canada and provided the very dry and warm conditions that set up and allowed those fires to become so large and devastating. So I'd say that the effect of the jet stream on air pollution is much larger than the effect of air pollution on the jet stream.
Thank you so much for that. It's really fascinating to see how, as we said, and as is so obvious to me, everything affects everything.
So one of the striking features of present day conditions is the enormously large temperatures in the North Atlantic Ocean. The sea surface temperatures are pushing 4.5 standard deviations above the norm. Now, I know that James Hansen is convinced that it's the tightening of sulfur restrictions by the International Maritime Organization that's reduced sulfur over the oceans. So there's less cloud condensation nuclei and noticeably less clouds and more absorbed solar radiation in the water. I mean, that's one of the reasons, but also, I mean, do you know if there's been persistent ridges over the North Atlantic, which would lead to warming? And I guess that leads to another question is, do we know much about the jet streams, how they would respond if we had the AMOC to shut down, for example? That's been in the news a lot, the reducing ocean current. So how's that going to rewire the jet streams? And for that matter, do we know much about jet stream configurations in the past? For example, in 20,000 years ago, the peak of the ice age, coldness. Do we know much about the jet streams back then at all? I mean, is there any good papers on that you know of?
So starting with your last question first, there have been some studies that have tried to look at proxy information. So indications of temperature anomalies, precipitation anomalies that can be linked to jet stream patterns, but we don't have actual observations of the atmosphere back then in terms of where the jet stream was actually located or what was going on any particular day. But we can look at these shifting patterns of indicators of heavy precipitation or drought or high temperatures, different plants that grew or animals that in lake bed sediments and things like that they've been able to look at, what looks like might be jet stream patterns. And we know that during ice age conditions, the jet streams were much stronger because those north-south temperature gradients were much larger. That's pretty straightforward. But getting to your more present question about what's going on in, say, the Atlantic Ocean, my answer would be anything that affects temperature differences between one place and another place, whether it's the north and the south or the east and the west, is going to have an impact on the jet stream, because the jet stream is created by those temperature differences. And the bigger they are, the stronger the jet stream will be. And wherever they're located is going to determine where there are ridges and where there are troughs. So having all that warm water in the North Atlantic, as we see right now, does tend to put ridging there, or it favors the existence of ridging in especially the polar jet stream, but it's also helping to strengthen the subtropical jet stream. And we know that as that AMOC, as you described, the Atlantic Meridional Overturning Circulation, which has been in the news a lot lately in terms of it slowing down, is having an effect on the temperatures of the North Atlantic. And again, anything that affects those temperature patterns is going to have an impact on the jet stream too. So we see warm water piling up along the eastern seaboard. That's been happening for several years. We see this pool of cold water sitting south of Greenland called the cold blob, another very technical term. And all those things affect where the jet stream is and the impacts of the weather associated with wherever the ridges and troughs in the jet stream lie. So especially downstream of some of these features like the cold blob, there are some new papers looking at weather patterns, especially in Western Europe. And the indication is that if that cold blob persists, which we expect it to do, we'll see a general troughing in that region, which will mean that downstream of that, the storm track will be heading up into more Scandinavia and leaving the UK and Western Europe more in the dry. And that's, kind of what we've been seeing, is a tendency for more heat waves and droughts in Western Europe and even in the UK. And it could be related to this existence of the cold blob, which is connected to the slowing down of the AMOC.
Thank you. And my very last question for you, it's kind of tongue-in-cheek. You testified to Congress in 2019 at something called the State of Climate Science and Why It Matters. Do you have pleasant memories from that? And do you think it made a difference? I mean, are you gonna, is that something that might happen again?
Actually, I've testified 3 times, twice for Senate committees and once for a congressional hearing committee. The first time was back in 2014, I think it was. That was a very disturbing experience, because what I observed was that one side of the aisle had their witnesses that were on one side of the climate argument, and the other side of the aisle brought their witnesses, and the two did not listen to each other at all. So while I was testifying, I could see the other side of the aisle, looking at their emails or leaving the room, not paying attention, just having a chat. And it was really disturbing to see how little one side was listening to the other side. The second time in 2019 was a better experience. The discussion then was not whether climate change was real or human caused. It was more about the discussion, and the arguments were more about what we're going to do about it. So that felt like a step forward. Yeah, so it was an interesting experience, very interesting.
Thank you.
You've given us a little bit of hope there, Dr. Francis. The fact that people in the US government are starting to actually believe in the science and the reality of climate change. I've heard a lot less decrying of climate science now than I've heard, 20 years ago or even 10 years ago. So I think perhaps now that maybe it's too late, there's a sign of hope that people understand what's happening. I know it's a rather cynical comment. Would you say that it's too late, or is there any way to make things better?
It's never too late, because we can always make it better than it would be if we didn't do something. So, the best time to attack this problem was 30, 40 years ago, but today is the next best time. So anything that we can do to reduce the amount of heat trapping greenhouse gases in the atmosphere is going to make it less bad in the future. And so we're going to have a lot more extreme weather. There's no doubt about that. We're going to see sea level rise continuing, and that's a tough train to turn around, but we can still make it less bad. And we need to be pulling out the stops in terms of reducing those greenhouse gases everywhere we can. And I do see hope because I do believe that the public has experienced the effects of climate change personally at this point. It's been hitting their wallets, it's been affecting their livelihoods, it maybe even injured their families, their communities, but they are experiencing it personally. And that, I think, while it's horrible, is actually waking people up. And so there is a silver lining to all this extreme weather that we've seen. It is waking people up, and I think there's a lot more people who are feeling like we've really got to do something, and they're stepping up, especially at the community and state levels. At the national level, it's still a challenge.
Yeah, can I just say that I think it's so important, the scientists, and you're very good at this, of communicating extreme weather events specifically. I think the scientific community, for good reasons, has been very slow on taking a lot of time to sort of prove that extreme weather events are happening, increasing, and are damaging. The sixth assessment, I think, put that to rest and told us that they are increasing, the human caused, and they will continue to increase. But hearing you say that the public, particularly in the United States, is becoming very aware. I remembered that last year, 2023, NOAA has this a program where it gives us the number of billion-dollar weather and climate-related disasters affecting the United States. And last year was a big record by far and away. So yeah, it's happening. Unfortunately, we're being hurt because of the I don't know how words don't describe how the politicians are doing worse than nothing.
So I absolutely agree with you, Peter. Scientists are now realizing that it's a very important part of our jobs to explain our work to the public, which most of the time are funding our work. And I think it's a very important thing that we are able to speak to public audiences about all sorts of things, whatever it is. But I think in the case of extreme weather, it's particularly important because people love to talk about the weather. We know that, right? And so when there's an extreme event, it's an incredible opportunity to hook somebody, start talking about it at that extreme event. And then I like to call it slipping some spinach into a cheeseburger, because you've got this cheeseburger that they're all excited about eating. And then that spinach is some information about how that extreme event was connected to the climate crisis. And that way we educate the public when they're paying attention and they're learning while enjoying that cheeseburger. So I think science communication is very important. And I think this next generation of scientists coming along understands that, and they're getting training while they're graduate students, where, when I was a graduate student, that was never the case. So the world is changing, and in that sense anyway, for the better.
The IPCC last two assessments makes this absurd statement that the melt and the loss of Arctic summer sea ice is reversible. I know where it comes from. It comes from, I think just one paper that I'm aware of, that there's a model that they ramp CO2 up and they ramp it right down. The ice melts, and guess what? The ice freezes again. But I'm really, really concerned about this, because also I've noticed that the scientists are missing that out. On the tipping points, for example, they don't have the summer sea ice. They have the winter sea ice. I think this is one of those terrible aspects of modeling, which is, talk about not helpful, it's decidedly unhelpful. I guess you've noticed this.
Yeah, the models don't do a great job of simulating how the sea ice behaves, especially in terms of the heat that's being transported by the ocean, because that is a difficult thing for them to capture. They underestimate it, and we know that it's increasing. And so even if we were able to cool the atmosphere somehow, there'd still be a lot of heat being transported by the ocean up into the Arctic. But I agree with you that it's the message that comes out of that is very unhelpful. It kind of takes the pedal off the gas in terms of worrying about the sea ice. And I think, if it could eventually grow back. I mean, it has in the past, we know, but it takes a pretty extreme set of circumstances to turn some process like that around, because there's so many factors in play. And especially that long-term input of heat from the ocean, which is not going to be easy to turn around.
Has anybody got any idea or intuitive ideas? If we go to cooling, which we're going to go to cooling because the corporations and the leaders are only going to keep on extracting fossil fuels. What does that have on ocean heat, deep ocean heat? Do any of us have any idea? I can't find anything about it.
When you say cooling, you're talking about solar radiation management cooling, Peter?
Yeah.
Yeah,
Which
okay.
clearly,
and by the way, I've seen some models show that if the AMOC shuts down, the sea ice will extend almost as far as Ireland. So I don't know how valid that is, but you'll get lots of your sea ice back if the AMOC shuts down, at least on a temporary basis. And Jennifer, I loved your hamburger cheeseburger analogy, but I think you might have some complaints from the spinach lobby and the hamburger lobby.
Bring them on. That's all right. I'll talk to them.
Maybe you can adapt it, Jennifer.
So I want to thank you, Peter and Paul. As always, it's been such an interesting discussion. I love your questions and the points that you bring up. They're always so enlightening. And I also especially want to thank Dr. Jennifer Francis. This has been such an interesting show. I've really, really enjoyed it. I've enjoyed learning so much about the interplay of the various forces of the climate, the temperatures, how they all affect the jet stream, and how that in turn affects the weather. And thank you to Paul for bringing up the jets that were going over at 800 miles an hour. I saw that too, and I thought that was fascinating. Thank you so much, everyone, for joining us. And like I say, if you've not subscribed, what are you waiting for? Go ahead and hit that subscribe button and share with us your thoughts on the jet stream. How do you think it'll affect you and the people that you love? Thank you so much, and we'll see you next time at the Climate Emergency Forum.